So last class we were discussing about emissivity. I introduced you the concept of R emissivity and E emissivity, and why those two definitions came. And I also said that for almost all practical purposes, the definition of R emissivity holds good. Okay. So the basic equations I have given it to you. So this is what we have seen newly in the last class. Rest of the class all went in looking at the assignment. And the narrow band, broad band emissivity I discussed, and two equations roughly I have given here. So this you can use, and also there are plenty of other papers which helps us to use the spectral emissivities available in satellite data and convert it into a broadband emissivity of the entire 8 to 14 micrometer range. But just remember one thing here, even though all Earth surface features can emit in longer wavelengths continuously, say beyond 14 micrometers also it's going to emit, but in our case all these equations will be restricting the emissivity to 8 to 14. That's what we can measure. After 14 micrometers we don't have any satellite observations, still microwave. The atmosphere is totally opaque, we cannot do any remote sensing. So the emissivity, whatever emissivity we calculate using these broadband conversion equations, almost everything will limit ourselves only to 8 to 14 micrometers range and not more than that. But this should be sufficient for our purpose. You want to calculate like how much energy is going out of the surface for climate studies, hydrological studies and all. This equation should be sufficient. Okay, so where can we get emissivity data? Because we were repeatedly telling that emissivity is important, emissivity is important. Without emissivity, there can be errors. Like even in the assignment, you can just try. When you get free time, we calculated with the emissivity of the object and all, right? Just remove the emissivity and see how the temperature you calculate changes in the inverse Planck's equation. That will give you like a different result. So emissivity is kind of important, not kind of, really important. So definitely we should be needing some data source from where we can get this emissivity. Emissivity can be measured in laboratory conditions. There are specialized instruments available. I will show you some pictures in the coming slides. We can measure it in the field with some limitations, not extremely accurate measurements, but still useful measurements we can do in field also. But emissivity is as we already discussed, it's a property of an object. It's not going to change unless the object itself changes or the character of the object itself changes, right? So what people have done is they have developed a library of emissivity values. Spectral libraries is there. This remote sensing students I have introduced to you in the last semester remote sensing course also. But spectral libraries are extremely important in order for us to understand both the reflectance properties and using Kirchhoff's law, 1 minus reflectance is emissivity. Using that we can get the emissivity that we need. So almost thousands of objects are available. Just one of the libraries I have mentioned here in this particular slide. So just if anyone is interested, you can go to this website, register with your email ID. Within 1 or 2 days, they will send all the files. Everything will be like in a text file. You can process it in Excel, like open it in Excel and use it. So it's completely easy to work with the spectral library data. You can plot, you can see how emissivity varies. I will show some figures also taken from this library. Okay. And as I have already told you in the previous classes, when you want to, like the spectral library will be extremely narrow spectral, extremely narrow bands. Extremely narrow bands means they will be talking with, or they will be giving the data with very fine spectral resolution, say 0.001 micrometers and so on. Extremely fine when we compare with our regular satellites. So mostly we will be in a position, or we will be needing to integrate it. Let us say I want my satellite works in say 10.6 to 11.5 micrometers. Whereas this emissivity will be available like 10.601, 10.602, like this. We will have like plenty of values at each wavelength. They will give one emissivity values. So ultimately we will be needing to integrate it in order for us to get to the required bandwidth, and we should use some basic definition what we have already seen. Okay, so we should do numerical integration of emissivity, and then only we can get a band average. Okay, so just don't do a simple average of emissivities. Please do a proper numerical integration, at least using trapezoidal rule, and then get it. And one more thing, what will happen is sometimes we will be needing to compare between a satellite estimated emissivity and this spectral library. Let us say I have more emissivity from Aster data. Okay, Aster provides me emissivity in 5 thermal channels. Sometimes what will happen is we may have to directly compare the pixel values of emissivity with the spectral library. It can actually happen. When such things happens, it is not only enough if we just do a spectral averaging like this or integration like this. We should also integrate with respect to the spectral response function of that particular sensor. Okay, so spectral response function, I have already briefly introduced it to you. This is also available like for some of the common sensors like Landsat 7, Landsat 8, Sentinel-2. I have not seen for MODIS, but it should be available. The spectral response function is available from internet itself, like the satellite web page itself they provide. Maybe just one example I will show. This is I have downloaded actually from USGS website. So you can see how the spectral response function varies for each of the thermal band in Landsat 8. So the blue color line is for Landsat 8 band 10, red color line is Landsat 8 band 11. Okay, so this gives the number. So this is the actual spectral response number at this given wavelength. This is my spectral response. So that means where there is like a maximum, where there is like a high values, that particular sensor works pretty well in that band. Rest of the wavelength also it is observing. Let us say the efficiency of the sensor in observing wavelength at say 9 micrometers only 0.0007. Whereas if you look here, at 11 micrometers, its efficiency is 1. So whatever energy comes at 11 micrometer wavelength, it will measure it completely without any loss. Say at 11.05, it has 99% efficiency. So this is the basic information we get from spectral response curve, at which wavelength our sensor is highly responsive or not. And the bandwidth we define, like for Landsat, how the bandwidth we define is, let us say, we will always tell, okay, this band is between 10.5 to 11.5, 10.7 to 11.2. Like that, we will tell one bandwidth, right? That bandwidth also is defined from this particular spectral reflectance curve only. Just see here, like all the values are pretty less. Suddenly it will increase. Say here from 0.062, it's slowly increasing here. At one point, it will cross 0.5. Say here at 10.6 micrometers, it has crossed 0.5. And similarly, it will be again increasing and then it will decrease and it will fall below 0.5 at some interval. Say here. Okay, so it fell below 0.5. So for this particular sensor, the bandwidth what we will give is from here 10.6 to 11.2 micrometers. The bandwidth in which the spectral response is above 0.5. That is what we will say. Whatever is the wavelength range where the spectral response is above 0.5, we will call that as our spectral bandwidth. Okay, so for this particular channel 10 in Landsat 8, the spectral bandwidth is 10.6 to 11.2 micrometers. This is how we will normally say the bandwidth of the sensor. So what we have to do is say this is how the spectral response will look, and I'm preparing an assignment also. I'll post it to you soon. Yeah, so this is how the spectral response values will be. This will be like the emissivity values. Here I have just averaged the emissivities, but it will be at a much finer spectral resolution. So we have to use both of them in the integration. So multiply. One second. Yeah. So multiply the spectral response function at that at that particular wavelength into the emissivity at that wavelength into Planck's function of that object at whatever temperature we assume it, say 300 Kelvin or something. So the ultimate take home message is, when you want to compare the data from spectral library with any satellite based emissivities, we should always account for the spectral response function from that particular sensor. Else there are high chances that our values will mismatch. Okay. So this is like, please, when you find time, download the spectral library and play with it. Like, you can visibly see how it varies. Okay. So any question in this? Okay. So next what we are going to see is the emissivity spectra for few common earth features. In basic remote sensing courses, we will normally see the spectral reflectance curves, right? How spectral reflectance for vegetation looks, how spectral reflectance for water body looks, like that we will see. Here in this course, we are going to look at the spectral variation of emissivity, and just a very brief introduction just to give an idea how it varies. Okay. We will not discuss in detail why it is changing, where it is changing and all. I will just show you and tell some important points. That's all. We will see it in two parts. One, the emissivity of different objects in 3 to 5 micrometer range, and then emissivity of the same objects in 8 to 14 micrometers range. How they change, we will see in one by one. So this particular slide gives you the emissivity of water at 3 to 5 micrometers. So you can see basically in 3 micrometer range, emissivity of water is quite low. Quite low means, if you always look at literature, people will always tell emissivity of water is very high. It is 0.98, 0.99 and so on. But it is not the case in 3 to 5 micrometers. In 3 micrometer range up to this 3.3 or up to here, emissivity is well below 0.97, and here it is like very low, 0.96. Then only it increases and it reaches all the way up to 0.98 or something. That's all. So in 3 to 5 micrometers, emissivity is quite low, like quite low in the sense when we compare with the TAR band and what we see in literature values. That's the only thing I'm saying. Normally literature, they will say 98 and above, 0.98 and above. In 3 to 5 micrometers, it is not the case. And then it gives like a low value in 3 to 3.3 micrometers. The emissivity value is quite low, but the change is not much. It's a very smooth linear curve. You can see it increases with wavelength. It increases and it becomes kind of an asymptote after the say 4 micrometers. It stabilizes at around 0.98 emissivity value. So next is ice. Same, almost like very similar property for ice. And for ice, actually the emissivity value going low is very high in this 3 micrometer channel. So if at all you are doing a mid-wave infrared remote sensing with ice, be careful, the emissivity values is pretty low, 0.9 and all. So low emissivities, if you do a mistake in calculating it, the error in LST will be very high. Remember it. Okay. Let us say the emissivity value is very like around 0.98 or 0.99. There you do a mistake of, let us say, 0.01. It may not cause much error in LST. But for some objects, if the emissivity is very low, say 0.9 or less than 0.9, there you do the same error of say 0.01. The error in LST will be quite higher. Okay, lower the emissivity, higher will be the error in LST when you do even like a small error in calculating that emissivity. So be careful with lower emissivity values. And for ice also, the emissivity slowly increases with wavelength and then reaches a peak around this 0.98 value around this 4 micrometers. Okay, so both water and ice, they behave very similarly. Only thing is, for ice, the dip in emissivity is very high, like very sharp dip. The value decreases all the way up to 0.91, and both of the curves exhibit increasing emissivity with wavelength, and both of them becomes asymptote at 0.98 emissivity value. Same thing with snow also. Snow I have given both for coarse snow and fine snow. Coarse snow means like granular snow objects, and fine snow means extremely fine snow in the order of like few micrometers. Okay, so always finer the snow particles, that is smaller the size of the snow particle, higher will be the emissivity value. You can see in all the wavelengths it is the case. And then even this dip around this 3 micrometers, that is reducing. Okay, so that is not that high. And fine snow has pretty high emissivity value, above 0.99, especially in this 4 micrometer channel. Water. So now we have finished actually 3 to 5 micrometer part. So 3 to 5 micrometer part we saw for water body, ice and snow. Vegetation, I will show both 3 to 5 and 8 to 14 in the same slide coming by. So now we are moving to the 8 to 14 micrometer wavelength range. If you look here, there is like a slight difference in the pattern. Here also emissivity is very smooth, not much of variation. From 0.98, it's like the emissivity for water is well above 0.98. But what happens is, once it crosses this 11 micrometer range, it peaks out at 0.99 and then it starts decreasing. So this we have to remember. So for water body, or for generally water, in 3 micrometers there is a dip and then it increases and reaches a asymptote within this 4 micrometer range. When we come to 8 to 14 micrometers, emissivity is fairly high, well above 0.98, and it still keeps on increasing with wavelength, but that increase stops around this 11.1 micrometer channel, 11.1 micrometer wavelength, and then it starts decreasing. Okay, so it decreases, you see, it decreases all the way up to 0.96 for 13 micrometer channel. So what we have to remember is, normally when we retrieve LST, it is very natural for us to assume an emissivity value of say 0.98 or 0.992 water bodies. It's very easy to classify water bodies in remote sensing images. Okay, so we would have like seen like very easily we can distinguish water bodies. And what people typically tend to do is they will identify all the water bodies, assume a constant emissivity, say 0.98 or 0.99 to the water. But that assumption is valid only when your emissivity channel is between this 10 to 11 micrometers or 8 to 11 micrometers. After this 11 micrometers, it decreases. There are some sensors which works in 11 to 12 micrometer range. If that is the case, emissivity value, you cannot assume a constant value. There is like a good change in emissivity. It suddenly decreases. Okay, so we need to be really careful in which wavelength you are working. Okay, but most of the, since the value is always higher than 0.98, what most of the literature argues is up to this 12.5 micrometers itself, it's pretty safe to assume an emissivity of 0.98 for water body. That's the basic assumption all the literatures do. Because even if you are see at 12.5, though it is decreasing, but still the value is above 0.98. So that's the logic. If you assume 0.98 within the wavelength of 12.5 micrometers, you are safe. That's what people say. But be careful and look at the wavelength in which you are working. Assume emissivity values appropriately. But in our lab exercises also, when we do LST retrieval, we will assume 0.98 using the same assumption. It is fine, but be careful. Some sensors, it may give you well beyond this range also, like Aster and all. Aster sensor and all has emissivity or spectral bands even after this 12.5 micrometers. So there be careful. Emissivity values drops below 0.98. Okay. So this is for water. Ice also shows a similar pattern, like emissivity increases up to this 10.7 micrometers or 10.6 micrometers, and then it decreases suddenly and it becomes asymptote at around a value of 0.94. Okay, so here also you need to be careful. If you are able to, let us say people working over glacier surface and all, glacier surface or polar regions, again over ice they will assume some emissivity values when they retrieve LST. surface temperature. Again, you need to be careful which wavelength my sensor is, what is the emissivity value in that. So you need to look at the spectral library, get to know the value. Don't assume any constant high value. It may be erroneous sometimes, not sometimes, mostly it will be erroneous. Look at the wavelength in which you are working and then assume emissivity appropriately. So water and ice typically show like similar pattern. Only thing is the wavelength at which the decrease happens changes. For ice, the decrease starts happening at a much earlier wavelength, whereas for water, the decrease happens at a later wavelength, around 11.1. And the curve shape is also different. Like this comes like this, whereas ice, the shape is like this, convex and concave. The way they fall, it's different. Same pattern with snow also, not much of difference. Ice and snow, like especially this core snow, if you look, it reflects, or sorry, it emits very close to how ice will emit, but fine snow has a different pattern. Fine snow typically has very high emissivity range in this 8 to 14 micrometer channel. We can assume it to be like 0.99 and all. It's fairly constant without much variation. Whereas for coarse grained snow, the emissivity value changes with wavelength. Okay. And this follows pattern very close to emissivity of ice. And finally, we are coming to vegetation. Vegetation, calculating the emissivity is or plotting one single curve is not easy. Not easy in the sense we have different types of vegetation with different leaves, different seasonalities and everything. So plotting one curve for vegetation is extremely difficult. Okay. But somehow some general information is given. So this left side thing, it is 3 to 5 micrometers. Here it is 8 to 14 micrometers. So if you look at this 3 to 5 micrometer range, almost some basic vegetation types, conifer forest, deciduous, dry grass and all, they have extremely high emissivity values without much change, well above 0.99. Okay, very flat line without any change. But for dry grass, what is given here in this curve, the emissivity is very low. Like you can see in this range under it becomes 0.75. So what it means is, as vegetation dries out without water, its emissivity decreases drastically. So vegetation water content plays a major role in defining its emissivity value. So this is the case for dry objects. If you look at 8 to 14 micrometer range, the emissivity of all that like conifer or deciduous tree or grass, again everything is like fairly okay, like well above 0.98 continuously, like 0.975 or something like that. Again here for dry grass, it is getting lower, but it's not falling very low as 0.7. It's getting as low as 0.9. Okay. So the leaf structure, vegetation present, sorry, the water present in the leaf, all these things play a major role in defining the emissivity value. And some like conifer forest, conifer is like needle shaped trees. This needle shaped trees has pretty high emissivity throughout. Deciduous is mostly what we find in like our climatic conditions, especially in the southern part of India. So deciduous trees, they have like somewhat varying emissivity values, and sometimes it gets below 0.98, and grass has typically high emissivity value. So vegetation also has higher emissivity range, well above this 0.975, and it's much higher than that. But again, the amount of vegetation water content present will change the emissivity value. And one more thing you have to remember is the emissivity of a canopy will be different from that of a leaf typically used in lab measurements. So this one you always have to remember, like same property I would have told you in optical remote sensing also, like last semester remote sensing course. What did I say? when you measure reflectance of a single leaf and when you measure reflectance of multiple leaves like a canopy, the canopy will have higher reflectance, and I have told you why also, right? Similar concept applies here also. Emissivity of a single leaf and emissivity of a canopy will be different, and a canopy will typically have higher emissivities. Okay, so let us say a single leaf has an emissivity of 0.975. A canopy may have an emissivity of 0.98 or 985 and so on. It will be higher than the single leaf. It is again because of leaf multiple scattering that is happening, but emissivity of a canopy will be higher. Rough vegetation canopies has increased emissivity. Like rough vegetation canopies means like when you look from the top itself, you will get a feel whether the canopy is looking rough or smooth to your eyes, right? Same concept. If it is like a rough canopy with lot of variation in leaf structure, canopy height and everything, typically it will have higher emissivity range, whereas a smooth canopy will be what? A well-grown paddy field uh, or a grassland, like perfectly maintained grass field, everything will look smooth to our eyes, whereas a forest canopy may look rough. So smooth canopies will have lesser emissivity when you compare with rough canopy. And then vegetation water content play a major role in deciding the final emissivity. Higher the vegetation water content, typically the emissivity will increase. Okay. So finally, we are going to see about the emissivity of soils. Emissivity of soil, again, it's very difficult to generalize. Like there are like hundreds of types of soils in this planet, not hundreds, thousands of soil types in fact, and each of them has a characteristic shape, and they cannot be generalized. So what is shown here in this slide is for multiple soil types, like for hundreds of soil types for which the spectral library is available, people have just averaged it. So this curve shows an averaged spectral emissivity for different soil types. Okay, so this is not emissivity for any single type of soil, but for average for multiple soil types. It's a mean as well as a standard deviation. This thick line is the mean value. This thin line is the standard deviation of the emissivity of different soil types. So what are the different factors which affects the emissivity of soil basically is the mineral composition. What is the mineral or what is the chemical that is present in the soil, say quartz or carbonates, etc. Each one has their own reflectance property, and hence the emissivity also will be influenced. And based on how particular soil contains, say, quartz or other materials, its emissivity will vary drastically. Say, for example, soil, sand. Sand is fully composed of quartz. It will have completely different emissivity from clay. Clay doesn't have much quartz content. So each and every mineral that is present will totally vary the emissivity of that particular soil. However, in addition to mineral composition, the soil organic content and soil moisture influences soil emissivity. Soil organic content means addition of manure. So addition of manure or falling of, like, say, leaves over the soil and getting decomposed. All these things will change the emissivity, and typically organic soils will have higher emissivity than mineral soils. Mineral soils means non-organic soils, soils without much organic content. Okay, so that one thing is there. And then soil moisture also. Higher the soil moisture, higher will be the soil emissivity. So soil moisture and soil organic content play a major role in defining the emissivity value. And a few characteristic points that you have to remember is, you look at this curve. Wherever the mean emissivity value is lower, here it is low, here it is low, compare it to the other charts, the standard deviation is very high, like here. Like if the mean value decreases, the standard deviation increases. That means what it says is at this particular wavelengths, like 8 to 10 micrometer or 8 to 9 micrometers, and also this around this 3.7 to 4.2 micrometers, the emissivity values of most of the soil type is low, but many soil types shows very high variation values. That's what you have to remember. Like emissivity of soil in this 3.7 to 4.2 micrometers as well as 8 to 9 micrometers is quite low when compared with other wavelengths. But the variation between different soil types is also very high. Like some soil will have low value, some soil may have high value. You have to remember. So whatever is the soil type present in your area, you should work accordingly. But apart from it, let us say you cross this 10 micrometer range, again emissivity is fairly high, above 0.96. Okay. So this is what the basic, very basic information about emissivity for soil. So any doubts up to this? We have just seen very basic information, how emissivity of different objects changes with wavelength. Just go through it. Okay, so you go through the curves and some reference material I'll provide. So if you go through, it should be fine for you to remember it. Okay. Any questions up to now? Okay. So next thing what we are going to see is the angular variation of emissivity. That is, angular variation of emissivity means emissivity will vary with respect to the viewing angle of the sensor. Okay, so this is very close to what we see in our reflectance. Like if there is like an object, if you see from the top, it may look differently. If you see from the side, it may look differently, right? We have seen this property in reflectance. Reflectance changes when we see from different directions. Same thing will happen with emissivity also. When you look from different directions, the object's emissivity may change, will change mostly. Why? Because mainly what we call as the anisotropy of that particular material. Say for example, I have told you an example with vegetation, right? Say when you look from the top, you may be looking at the leaves, or when you look from the side, you may be looking at the mix of leaves and stems, branches. Sometimes soil will be visible. So what do you see will differ when you look from different angles, and same object may have different structure in the other side. Okay, so there is like a, let us say there is a building. The top building may have a different material, maybe concrete, whereas the side may have a different material, say glass or something. So the same building, when you look from different side, you are looking at different properties or different features that makes up that particular building. Naturally, the emissivity will vary, and that's why this angular variation comes in. And this curve shows how emissivity varies for different objects at different viewing angle from zenith. Okay, let us, zenith means we are calculating this angle. The object is here. What is this particular angle? Theta. Okay, zenith angle. Normally speaking, most of the objects has not much of a variation up to this, say 30 degrees of viewing angle. If you look up to this particular line, 30 degrees viewing angle, not much of a variation is observed, and variation starts happening only after that, and a lot of variation comes only when you cross this 50 degrees zenith angle, right? 50 degrees zenith angle means like the sensor is looking fairly wider. So for some sensors such as MODIS, which has extremely high scanning angles, this may be a problem. You have to take this into account. So when the sensor viewing angle crosses 50 degrees, emissivity change will be much pronounced. And among different objects on the Earth's surface, soil, typically sand, and then water has very high change in emissivity with respect to angle. They will completely look different when you look from different angles. That's the point. So water body, when you look from the top, its emissivity is very high. But when the same water body is observed by a sensor with a zenith angle of 50 degrees, its emissivity has decreased all the way up to 0.95. Okay. So water and soil shows very high change in emissivity values with respect to viewing angle. But for most other objects, it is okay. And then there's not much of a change within 30 degrees zenith angle. So if your sensor is only nadir looking, or the scan angle is very limited to within 30 degrees scan angle, it's not going to cause much change in emissivity value. This is like the main message you should understand. And the same thing is I have given here. A decrease in emissivity is observed in the 8 to 14 micrometer range for increasing viewing angle. That is, as the viewing zenith angle increases, the emissivity decreases. That's what we are observing. Different objects have different angular variation of emissivity. That is, if you look at this, the fall or the change in emissivity is varying for different objects. Here, this is like clay. Clay soil is fairly constant, whereas a water body, its change is rapid. Sand, the change is rapid. So different objects has different rate of change. That is the point that is given here. Structure of a surface can cause a change in the viewed portion of the objects. I told you an example, right? Like when you look from vegetation from the top and the side, you may get a different perspective. So that is what is given here. You may be seeing only the leaf, or sometimes you may be seeing the mix of leaf and soil. Everything will come into picture, changing the emissivity value. Surface slope and sensor scan angle can both combine to produce larger viewing zenith angle. That means till now we are talking only about the satellite viewing angle and assuming a flat surface. But let us say one second. Let us say there is like an object that is present on a slope. So for this particular sensor, the object may be having, combined with the slope of the terrain and the satellite viewing angle, for this particular object, the total viewing zenith angle will be much higher than what the satellite is looking. Let us say my satellite is only nadir looking, that is fine. But if my object is present on a slope, it is not anymore nadir looking. With respect to this object on the slope, we are getting an angle with respect to satellite, right? So if an object is on a flat terrain, the viewing geometry will be different. If the same object is present on a side of a slope or something like a mountain or mountain, it is going to change the satellite viewing angle. It is going to increase it most of the time. Mostly it will increase. When that happens, the emissivity value may go down. That's why there are a lot of studies which shows how emissivity or LST changes when an object is present on a mountainous slope or mountainous terrain. So this is also sometimes we have to remember.
Excuse me, sir.
And this is like for one of the point which I have told you, like especially for vegetation, what I said is when we are looking from different angles, especially vegetation, I said we will be seeing only the top of the leaves, or sometimes we may be seeing the side, looking at the stem or the soil, etc. Right? This curve actually tells you that. What this curve shows is variation of emissivity for a pixel composed of soil and vegetation. It has a mix of soil and vegetation a different vegetation cover fraction. The different vegetation cover fraction means within a pixel, what fraction of the pixel is covered by vegetation. Say PV equal to 13 means, PV is the notation they have used. 13 means 13% of the pixel is covered by vegetation. Rest all is soil. 48 means 48% is covered by vegetation. 83 means 83% of pixel is covered by vegetation. So what is like the main take home message from this particular slide is, higher the vegetation cover in the pixel, lesser will be the angular variation. Higher vegetation cover in the pixel, lesser the angular variation. You can see here like this curve, this triangle curve, just see here this line. The pixel is 83% covered with vegetation. So only very small amount of soil is visible, and when a sensor see from the top, mostly it will be seeing the vegetation. So only when the leaves are visible to the sensor, the vegetation of that particular pixel is fairly constant, all well above 0.98 or something. But when the vegetation cover is quite low, the emissivity change is quite drastic. You are seeing from say 0.952 all the way up to 0.98. The change is quite drastic here. Same thing happens with 48%. Still there is some change in emissivity value. Okay. So higher the emissivity content of a pixel, sorry, the vegetation content of a pixel, the angular variation will reduce. But if there is a mixture of both soil and vegetation, the emissivity will become quite complex to calculate and understand. Like when the viewing angle changes, emissivity also will change, because you will see different proportion of soil and leaves in different angles. Okay. So yeah, any doubts up to this point? Angular variation of emissivity?
Sir?
Yeah, go ahead.
Yes, sir. This emissivity, as we say, it is an intrinsic property of the object. Still, the state of the object is not changed, right? So by different viewing angle, it is changing.
Sorry?
For different viewing angle, it is changing, no, sir?
Yeah.
But the state of the object is same, right?
State of the object is same, but object within itself may show some differences, right? Like the mineral composition may change when you look from different angles. It can happen, right? It need not be homogeneous within inside. That's what I am trying to say. All object, even if it is one particular object, it will not be 100% homogeneous inside. There will be small heterogeneous within the object property. Even if you take like a tree, when it is viewed by a sensor, different portions of a tree will be seen from different angles. Same thing, if you take a brick or a tile, whatever object you take, it need not be 100% purely homogeneous. Always there is some amount of heterogeneity present in all natural objects that causes this directional change.
But in emissivity terms, sir, are we writing this viewing angle like is it a function of this angle, sir, in the emissivity term?
Normally in satellite remote sensing, we may not take this into account much. The problem is, if we have to consider it if we want a really accurate measurement, but sometimes we may go erroneous. That is one thing. Like when we do with simple algorithms, we may not consider this. But some sensors like MODIS, which has very wide scan angle, when they provide the emissivity product, they take into account this angular variation. They have this BRDF functions, how reflectance and emissivity changes with viewing angle. They have that mathematical model available with them. They take this into account and do. Yes. So for some sensors which has very wide scan angle, we must take this into account. Say MODIS or Sentinel-3 SLSTR sensor, they are all having very wide scan angle. But for sensors such as Landsat, which works only at nadir, we need not consider this much.
Okay, fine.
Yeah. Any other questions? Okay. Fine. So I told you before that we can measure spectral emissivity both in lab as well as the field. So I'm not going to describe how we are going to do that and all, but just I'll show you some figures of the instruments which people typically use. So this particular instrument is what is you are seeing in the slide. It is called a FTIR spectrometer. FTIR means Fourier transform infrared spectrometer. Fourier transform infrared spectrometer, and this is one of the setup which people typically use. Okay, so this is what we call as an this is like one half of a sphere in which the sample will be kept. So you can see here. So this is like there will be another half. When you combine both the halves in between, you will get a sphere-like structure. Okay, so this sphere you will keep the sample inside. So this sphere is called integrating sphere. You will keep the sample inside, and whatever is the energy available within the sphere, your instrument will measure based on which the emissivity or the reflectance, whatever will be calculated. So this is quite an expensive setup and difficult to maintain also. Setup is not available everywhere. If I remember correct, our Earth Science department in IIT Bombay may have this setup. I'm not very sure. I have heard they may have one such setup with them. Maybe have to check with them if it is available. But in most of the institutes or labs, it may not be. That's the case. A similar setup, a Fourier transform spectrometer, but capable of working in the field. So this is like a miniatured sensor to work in the field. Like this is now observing the emissivity of this grass from the top. This is a gold foil actually. Okay. They use it in the field, and this is again one type of spectrometer observing it. So this also we need to measure, like you need to use polished aluminum sheets or polished gold foil in the field along with the sample to measure. So you have any idea why this gold foil is here? If you look in this slide, here also there is some gold foil kept inside. Here also it is some gold foil is kept inside, or measurement is taken. Any guess why emissivity is observed over such gold foil kept in the environment in which you are making measurements?
The emissivity of the gold foil is negligible.
Sorry?
The emissivity from the gold foil is negligible.
Yeah, that is correct. Emissivity of gold foil is negligible. So
it won't affect of the surrounding like where it is kept. It will give only the objects for which we are taking the observation. Is it?
okay. So the main reason we are using this gold foil or highly polished aluminum foil also will be used sometimes. It is to calculate the thermal radiation from the surrounding environment. The thermal radiation from the surroundings. What happened to my pen? Yeah, that is, let us say this is like my surface. Its own emission is what I want to measure, but we have already seen there is always some spectral emission from the surrounding environment, say atmosphere, which will come down, fall on the surface, and it will get reflected. This we need to account like that. Let us say you have a sensor placed here, like this sort of handheld instrument. The energy that it measures, it's not only coming from this object, but also from the reflected energy coming from the atmosphere. We need to measure this, and we have to subtract it what the sensor measures. Whatever the sensor are measured, we need to subtract this atmospheric component. Then only we will be able to see what is the actual emission by the object of interest. This gold foil will give you this what is the amount of energy that is coming in from the atmosphere, because it has very low emissivity on its own. So whatever the energy it is coming out of it is purely, we can assume it to be purely the reflection of what is coming out from the atmosphere. Okay, so this will give you the incoming thermal radiation from the atmosphere in order to correct these observations. That's why we use gold foil. Gold foil has very low emissivity in the thermal band, very low emissivity and very high reflectance in thermal channels. That is why we are using it as a one of the tool for correcting the atmospheric effect. And this is another setup called box method. This is used to measure broadband emissivity. Broadband emissivity is slightly wider than what this FTIR gives. FTIR will give you like very fine spectral variation like 0.001 micrometers and so on. Box method will help you to calculate emissivity at a much wider bandwidth, say 10 to 12 micrometers, 11 to 12, like that, a broad band it will use. So the same sample, you have to keep it within the box. The inside of the box is a highly polished aluminum surface. Highly polished aluminum will be there inside the box. You need to have different lids for the box at different temperatures, cold lid, hot lid and all. So it's a quite laborious procedure. I'm not going to describe, but this method is also available. This is fairly cheaper when we compare with this FTIR, but less accurate also. Not that accurate, but many studies use this box method for field measurement because as it is very cheap, you can build whatever is needed within your lab itself. It's easy to build this structure. So that's why many people will use this. So main thing what I want to convey is measurement of emissivity is possible either in lab or in field with some specialized instruments, and using this sort of FTIR spectrometers only, the spectral library has been created and it is made available to us for us to use. Okay.
So this FTIR inside, in FTIR, what do we observe in the first hand, or then we have to calculate something, or is it directly it will give the emissivity of the object?
What? Can you please repeat? I'm not hearing clearly.
In the FTIR, sir, what we are going to observe initially, then we need to calculate for the emissivity, or it will directly give the emissivity of the object?
Most of the FTIR will give you the reflectance. Okay, even in thermal channels, it will have a own thermal source inside also. It will give you mostly the reflectance. So emissivity you need to calculate as 1 minus reflectance. That's what it will give. Even if you look at the spectral libraries, they would have listed reflectance values only. But you can, I think there are a lot of customization available. You can change the option. You can directly get emissivity also in some models. It is available. Yeah. But I think it will directly give. I have not worked with such FTIR because it is very limited in availability. But as far as my understanding is concerned from literature review, it is customizable. We can ask it to give directly the emissivity also.
I was curious to know that how this reflectance is this Fourier transform is being used in that.
Yeah, even I don't have practical experience working with it. Wherever I studied or worked, I haven't come across an FTIR which is accessible to me. That's the problem. That's why I'm not even explaining it to the full working principle. Unless I get a working principle or experience, I cannot teach you fully, right? That's why I'm stopping. Maybe in future, if I get access somewhere, I'll try to include it. Yes.
Fine, sir. Thank you.
Yeah. Okay, so I think with this, we finished this emissivity part. So finally, in this slides, we have seen different definitions of emissivity, like R emissivity and E emissivity, narrow band and broadband emissivities, emissivities of few objects on the Earth's surface, how it varies, and some very basic information about how emissivity can be measured in field or lab conditions.
Just one query, sir.
Yeah.
If the surface is not Lambertian, then the emissivity will be more in general.
No, if the surface is not Lambertian, the emissivity will vary a lot with viewing angle. It will not be more, or some angle it will be more, some angle it will be high.
I mean to say, sir, like for a particular viewing angle, if we are comparing a Lambertian with a non-Lambertian for a particular viewing angle, then it will be more than that, a Lambertian surface.
No. That's what. Okay. Typically, if you look at like a non-Lambertian surface, let us say this is like a Lambertian, this is like a specular surface, which is non-Lambertian. A specular surface will have one particular direction of reflectance, other directions it will be low, right? So if you measure emissivity from this particular angle, a specular surface will have very low emissivity because of its high reflectance. But if you look from some other angle, it may have higher emissivity than Lambertian also. It is possible. So that's why I said for a non-Lambertian surface, the angular variation of emissivity will be much higher because at only one particular viewing angle, it has very high reflectance and low emissivity. From all other angles, it will change drastically. That's why I said.
For a satellite, satellite-based image, we need not to we can't consider this thing, right?
We cannot. Normally, we assume a Lambertian surface. Even in our spectral radiance equation in Planck's function, we would have simply divided the Planck's function by pi, assuming the surface as Lambertian, right? That's the limitation we have. Yes. But some algorithms consider this viewing angle, like people have developed mathematical models to look at this emissivity, but like how emissivity will change with viewing angle. But modeling whether a surface is truly Lambertian or not is highly impossible from satellite scale. Very difficult. True. Okay. So this particular topic I stop. I'll start the next topic. Okay. So the next topic we are going to see is atmospheric correction, CA sensor calibration and validation. So these things we will see before we move on to the actual retrieval procedure, how to calculate LST. We will see it later, but these are some basics I wanted you to know before we move there. Okay. So first part, the general procedure to get radiometric temperature from satellite observation is normally, mostly we will directly, some sensors directly provides us temperature products, but for some satellites it is not available. Let us say the sensor is not providing a temperature product directly. We have to calculate. So what are the general procedure we will follow? We will take the satellite data. The satellite data will most likely have digital numbers, DN values. The DN values, we need to convert it into radians using the metadata file available. Like mostly you would have done it in previous year remote sensing course. Those students who study the remote sensing lab, you will be knowing how to use the metadata file to convert between DN to radians value. The constants will be provided there. Once the radians is available, we need to do atmospheric correction of the radians, and then we will estimate emissivity and LST using different retrieval algorithms. And finally, we must validate it. Whatever the LST you retrieve, you must validate. Without validation, we cannot be really confident about what we have done. Okay, so it's needed. So in this particular topic or the set of slides, we are going to see this part, very much basics, what atmospheric correction is and why it is needed. That we will see. We will see what is.
Yes, sir. In the validation part, you need to include the ground validations or?
Yes. I'm talking about ground validation. Yeah.
Okay. And sir, after this atmospheric correction, you will get the reflectance, right?
No, we will, after the atmospheric correction, we will have atmospherically corrected radiance. From that, we will estimate emissivity and LST.
Okay.
I'm talking about thermal channels.
No, because in normal, after this atmospheric corrections, we get reflectance image, right?
Yeah. Optical remote sensing, our ultimate goal is to get surface reflectance. So there we will do atmospheric correction and then we will land up in reflectance. In thermal remote sensing, after atmospheric correction, we will try to estimate temperature.
Okay. Yes.
Okay. Yeah. Here I am talking about this 8 to 14 micrometer range. No concept of reflectance is there. We are talking about temperature. Okay. So what I was telling, atmospheric correction, we will basically see what it is, why it is needed. Then we will see what is called sensor calibration, which is extremely essential in this part. When we do the DN to radians conversion, sensor calibration should be done, and finally validation, how it is done. Three parts we will see in this particular slide. This part, estimation of emissivity and LST, will be the topic for the coming lectures. First, we will start with atmospheric correction. This is the basic equation of the radiance reaching the sensor. The radiance reaching the sensor, I've already told you before, it consists of three major parts. One is the direct surface emitted component. Second thing is surface reflected atmospheric emitted thermal radiation, which will go toward the sensor. Both of these will pass through the atmosphere, and the atmosphere will allow only a portion of them, because this is atmospheric transmissivity. So both will travel together for the entire atmosphere, and the atmosphere will allow only a portion of it to go out. Say if the transmissivity is 0.75, only 75% of this energy will go out. Rest 25% will be either absorbed or scattered within the atmosphere. Okay. And atmosphere also has its own thermal emission, which will directly go towards the sensor. This is called path radiance. So three major components are there: atmospheric path radiance, atmospheric transmissivity, and the atmospheric emission that is coming toward the surface that is getting reflected. These three parameters we should know in order for us to correct the radiance observed by the sensor. Unless we correct for it, we are not going to get the correct temperature for the surface. So this particular slide gives you the effect of lack of atmospheric correction. What will happen if we don't do atmospheric correction on LST retrieved from satellite data? On y-axis, you have what is called like the difference between the true temperature of the surface. Like this is the true temperature of the surface measured from ground observations. Ti is the temperature you estimate from satellite. And this y-axis gives you the difference between the true temperature and the satellite estimated temperature. X-axis is true temperature of the surface, and these lines are for different atmospheric conditions. You see, this is like what we call as a mid-latitude winter. It's like within atmospheric models, we have some standard atmospheric conditions. Like this will be the temperature, this will be the water vapor content, etc. That sort of information will be there. So using that average data, people have done it. If the water vapor content is quite low, like W is the water vapor content, how much gram of water present per centimeter square of atmospheric area. Okay. Water vapor content is quite low. Atmosphere is very cold. 272 Kelvin means freezing conditions. So a winter in mid latitude. Mid latitude means say 30 to 45 degrees of latitude. Under such dry, cold atmospheres, dry means without much water content, and then colder atmosphere, the error is varying between -1 to +1 Kelvin. Not much, because the surface temperatures also will be very low at winter conditions. Within that range, your error is quite low. Look at the other end of the spectrum, the exact opposite, the tropical atmosphere. Tropical atmosphere means atmospheric conditions which we expect very close to equators, like 0 to 23 degree north latitudes, basically. Those tropical atmospheres will be characterized by very high water content, water vapor content, and higher temperatures, atmospheric temperatures. Surface also will be pretty warm, like tropical climates, like when we go to like southern India or Sri Lanka and all, we would have experienced like tropical climates. It will be like warm, humid. So warm and humid conditions. Warm, humid conditions, what is happening is error will be extremely high if you don't do atmospheric correction. That too, as the surface temperature increases, the error value or the difference between the true temperature of the surface and what you get from satellite will be much higher. Okay. That means higher the water vapor content and higher the atmospheric temperature. If you don't correct for atmospheric effect, our satellite will underestimate the temperature. This point, please keep in mind. If we don't do atmospheric correction to satellite image, the LST that we will retrieve will be highly underestimated. Okay, especially for much higher water content and high temperature. Here, if you look here, the error it is positive. Only for very cold or dry atmosphere, the error is negative. For almost all the positive temperature conditions, like above 0 degrees Celsius conditions, our satellite will underestimate the temperature, especially in tropical atmosphere. So you remember that. Next thing what we are going to see is a mid-latitude summer. Mid-latitude summer means water vapor content is in between both of them. Temperature is quite high. Like it's not very close to 0. It's close to say 25 degrees Celsius. There also you will get higher errors in temperature. Sorry, higher errors in temperature you get from satellite. So the basic thing you have to remember is hotter the atmospheric conditions and higher the higher the atmospheric water vapor content, there are high chances of getting underestimation in satellite observed LST. Okay, so if the atmosphere is cold without much water vapor content, then the error may be less. So this is like the basic message. Warmer the atmosphere and humid the atmosphere, we must do atmospheric correction, else we will be underestimating it. Okay. So here there is one point where we are overestimating it. Like my satellite LST is higher than true surface temperature. At what atmospheric condition you expect this to happen? Any guess you can make? Like what I said is here the atmosphere is warm, surface is also warm. You are kind of like underestimating the satellite LST. But this point here, the lower end of point, we are overestimating satellite LST. At what condition it can happen? Any guess you can make? When we will overestimate satellite LST if we don't do atmospheric correction? You guys getting the question? Why everyone is silent? You guys are there or not? I cannot see.
Sir, where you drawed in that slide, we did not see that point when you asked the question red color.
Okay, so here, if you look at this tropical atmosphere, what I described, I said when the atmosphere is warm, surface is warm, and when the atmosphere is humid, the satellite LST is underestimated. I said, like the errors are all positive. In this case, I am getting an error which is less than 0. That means my satellite LST is higher than ground temperature, the true ground temperature. In which condition it can happen? Mostly I said in general, the satellite will be underestimating LST when we don't do atmospheric correction. But in one example, there is an overcorrection which has happened. When it can happen, any guess?
It is very dry.
Temperature is very low.
Temperature is very low, fine. When atmospheric temperature is more than surface temperature, say here if you look, the surface temperature is 260, 265 Kelvin and all. Atmospheric temperature is 272 Kelvin. That means the surface is completely covered with ice or snow. its temperature is very low. Atmospheric temperature is higher than the surface temperature. This is what we call as an inversion of atmosphere. Normally, what we will observe in our climate conditions, surface temperature will be high, atmospheric temperature will be low, air temperature will be low. But when the surface is covered with ice or snow, the reverse can happen. Air temperature will be higher, surface temperature will be lower. Under such cases, if you don't do atmospheric correction, then you will end up in overestimating LST. Whereas if both of them are pretty high, not freezing condition and all, the surface is warm, atmosphere is humid, then most likely we will be overestimating it. Sorry, the LST will be underestimated. Okay, so that's the point I'm trying to make. Okay, so if the air temperature is hotter than surface, our LST may be overestimated. Or if the surface itself is pretty high temperature, it's warm, our LST may be underestimated. That's what I am trying to say.
In other two also it is similar, no sir? In mid latitude,
it is similar, but it is very close to zero. It is not kind of like coming to negative. That's the point. It's not. It will not come to negative line because surface is not freezing. Surface is pretty warm in that condition. Okay. As long as the surface is pretty warm, we will not be LST will not be overestimated. That's the point. But if the surface itself is like very cold, air temperature is much higher than it, then our LST may be overestimated. That's what I'm saying.
Got it.
Yeah. Okay. So how to do atmospheric correction then? Atmospheric correction is needed. We saw one example of different plots telling that atmospheric correction is important. Else we will be underestimating LST or overestimating LST. How to do? We will use what is called a radiative transfer models for doing this sort of corrections. Some radiative transfer models are free, open source, like this RTTOV. Something called Motran, which is we should pay some money to buy it. Actually, we have one license of Motran available with us, but unfortunately, you cannot practice it because it's there in only one system. All of you cannot access, but I'll try to provide a demo how it works. Maybe next week or 2 weeks later, we'll try to get a demo. What this sort of RTMs will do is, RTMs are basic models of atmosphere, and it knows how radiation will pass through atmosphere for different conditions. Given the air temperature, water vapor content, and other atmospheric like aerosols and dust, if you feed the data into it, it will tell you what will be the transmissivity, what will be the downwelling atmospheric radiance, what will be the path radiance, etc. And nowadays, almost all the RTMs are extremely accurate. Like people blindly use them because it is well tested, well developed. We can blindly use it without any doubts in our mind. So this RTMs always comes to our rescue for doing this atmospheric correction, but it cannot run in our normal laptop or desktop. It needs some sort of high computation power. Like a good workstation should be there to run this. Okay, so this is there, and some of it are free, some of it are with a cost. So this RTM, when provided with atmospheric data at the time of satellite overpass, it will give us the 3 parameters which we need: transmissivity, downwelling radiance, and path radiance. All the 3 it will be given. And also we should provide it the sensor spectral response function. What is the sensor? What is the spectral response function? We should feed in the this particular RTMs. Like some will be inbuilt, like Motran and all, like this Motran software and all comes with Landsat spectral reflectance inbuilt within it. But for some other sensors, we may have to give the data to it. If we give, it will modulate and give the output to us. So some of the key atmospheric variables that will affect the radiation are water vapor, carbon dioxide, ozone, and atmospheric aerosols or dust particles. They are like the very good absorbers. Of these, like water vapor, CO2, ozone and aerosol. The most problematic two are water vapor and aerosols. Other two, carbon dioxide and ozone, they are all well mixed within the atmosphere, like oxygen, nitrogen, CO2, ozone, everything is like well mixed. Whether you measure in Mumbai or you measure in Sri Lanka or you measure in London, the general ratio will be very close, very much same. But water vapor and dust, it varies a lot locally from one area to another area. The water vapor content in the atmosphere will vary. The dust content of the atmosphere will vary. So these two are the critical components. What is the water vapor content? What is the aerosol content of the atmosphere? If we can measure that and feed it into the radiative transfer model, we will be able to model the atmosphere pretty well. So how to get atmospheric conditions, how people typically do it? We can do either using ground observations. So normally the ground observation of atmospheric condition is carried out using such weather balloons called radiosonde. Okay. So it will carry sensor something like this. So this is like a very small miniatured sensor available. It will be tied to a balloon and sent up into the atmosphere. When it goes up, as it's going up, it will collect its location information through GPS, like at which height it is, X, Y, Z, it will collect. And what are the different atmospheric parameters like pressure, humidity, temperature, water vapor content. Some will go with like CO2 measurement and everything. So everything will be measured. And then after some time, this balloon will come back with all the data in it. So this will provide you the total variation of atmospheric conditions at that particular time when it is launched. Okay, so when the balloon launched and before it comes down, it will measure all these variables, store in it or transmit to us. In addition, like I'll describe thing maybe later, like in next class. In addition to this sort of like weather balloon, we also will have numerical models of the atmosphere. Okay, that is available. Like all of us may not have access to this weather balloon data. So we can also use numerical models which gives the data once every say 3 hours, once every 6 hours. What is like the different atmospheric characteristics, it is available. Okay, so this sort of numerical model data is available freely for download. You can download and use in your algorithm, or it's also available to directly use in Google Earth Engine. Some example are like ERA 5, NCEP, NCAR, IMDAA, MERA 2. Even like you can set up your own model called WRF. So these are some of the models which is available freely. You can just download the data and use in your algorithms. Okay, so either you can use ground-based observations from weather balloons, or you can use model data sets for collecting the information about the atmosphere. Yeah, maybe we'll stop now. It's 10:55, and then we'll continue in the next class. So any questions? Okay. So maybe if there are no questions, we will stop the class, and the deadline for assignment is changed today evening. So before 5 o'clock, whoever has not submitted the assignment, you can submit it. Okay. So with this, we will stop. And Chiranjeev, you asked a question, right? I think about the integration. You only asked, right? Last class.
Yes, sir.
I think the unit still will contain micrometer, Chiranjeev, like the wavelength. Even though we are integrating, as I said, still we are talking about one particular wavelength channel. So physically speaking, that wavelength should be there. As you rightly said, when we integrate, that term will vanish, but still for physical purposes, people write that unit micrometer with that, Chiranjeev, always. So I think you also follow the same convention. I saw your assignment. You haven't mentioned it, but you can mention the wavelengths here after the units. Okay, so it's watts per meter square per stadian per micrometer.
Okay, sir.
Yeah, Okay. So yeah, maybe we'll stop now. We will see again on next Wednesday. So thank you all. Have a good weekend. Yeah. Bye.
Thank you, sir.
Sir,
Thank you, sir.
Yes, Sakshi.